Okay, continuous valued random variables. Continuous valued random variables are basically random variables that take real numbers as their values. Can someone give an example? How about the temperature? Temperature is it's a real number. It doesn't take any discrete, any particular value. Any other examples? Speed of a car. Something like that. Pardon me?
Time?
Time. Time's a good one. So the time it takes, for instance, standing in line to the bank, the time that takes. Time. There's actually a huge body of research on queuing theory, which you may have heard a bit about. So the problem with a continuous random variable is that if it's taking real numbers as its as the elements over which it's taking values, then I can ask some fairly weird questions, such as, what's the problem? Let's say T is the temperature. Then I can say, what's the probability that T is equal to, let's say, pi? So pi goes on forever, so in order for the temperature outside to be exactly equal to pi, the temperature would have to match all of those digits. So what do you suppose the probability of that happening is?
Zero.
It's zero. It's basically zero. So suddenly this doesn't make any sense. So each particular real number, if I give you a real number out to an infinite number of decimal places, it seems like the probability of that is zero. But if I tell you in fact, here's another example. What's the probability that the temperature is exactly 5.00000, exactly 5 degrees? Again, that's zero. But this seems weird. So we know that things can have temperatures, so it seems like it should be possible that it seems weird that the probability is always zero. The problem is when we think of continuous valued random variables, we think more in terms of ranges. We think more in terms of what's the probability that the temperature is about 5 degrees, or within a couple degrees of 5 degrees. That has a non-zero probability. So to describe that, we use what's called a probability density function. The probability of events is described in terms of the probability density function, like so. So let's say we have a random variable x, probability density function f of x. We usually use f rather than p to talk about probability density function. Then what's the probability that x is between, let's say, -1 and 1? The probability of that event, which I'll write this way, probability -1 less than or equal to x less than or equal to 1 is equal to the integral from x equals -1 to 1 of f of x dx. So in other words, if f of x looks like, I don't know what it would look like, but let's say like this, then the weight under f of x on that range, the area under f of x on that range is the probability. So that's why this is a density. So the amplitude of the probability density function doesn't really tell you anything about instantaneous of the probability of any particular value, but it tells you where things are concentrated. So for instance, if my probability density function looks like that, then things are much more likely to happen there, or within close ranges of there, as opposed to out here. Within close ranges of that, things are fairly unlikely. Expected value and variance of continuous valued random variables are calculated basically the same way, you just substitute the integral for sum. So expected value. For instance, the mean expected value of x is the integral over x times f of x dx. The variance expected value of x minus, let's call this mx again, sigma squared x minus mx squared, the integral over x minus mx squared, f of x dx, and once again you can show that this boils down to expected value of x squared minus mx squared. Okay, as an example, let's talk about the uniform distribution. So x is a random variable, and f of x is equal to 1 if 0 is less than or equal to x is less than or equal to 1, and 0 otherwise. So this is what the PDF looks like. By the way, I forgot to mention, probabilities have to sum to 1, and PDFs have to integrate to 1. So that's let me write that over here. For all PDFs, the integral over x of fx is equal to 1 for all probability mass functions. The sum over x, p of x, is equal to 1. So that's a fundamental property of probability. If something is probability 1, then that means it always happens. So the interpretation of this is that all of the events together, something must happen. So all of the events together, the probability of that of something happening is 1. Okay, so over here, this satisfies that rule, because if I integrate this from 0 to 1, the area under this curve is quickly 1. It's basically a rectangle, or a square of height 1 and length 1. Okay, firstly, what's the probability that x is greater than 0.5? What do you think it would be? 0.5. It would be 1/2. We can write it out. There's no upper bound here, so I would integrate from x equals 0.5 to infinity. F of x dx. So to integrate from 0.5 to infinity, I first have to integrate from 0.5 to 1, over which the function is valued 1 dx, plus the integral from 1 to infinity, over which is valued 0. So that's a 0, and that's 1/2. So this is 1/2. How about